Let's dig a little deeper into how data on the computer is actually represented as binary, as ones and zeros. We talked before about the fact that data is represented as ones and zeros, and we showed a little bit about the decisions that we make with how much space to give data and what structure to represent that data, like a floating point number needing several pieces of information, that those impact how much we can store. And we've even seen in the past that there are codes and systems for representing things that are not numerical as numbers, but what we haven't yet put together is how those numbers are actually stored as binary. So we know, for instance, that a character in a string can be mapped to an ordinal value, which is an integer. Today, let's look at how those integers get turned into a binary representation. So understand that binary is a system of counting, just like decimal that you've probably used all your life, but where decimal has 10 digits, 0 through 9, at any given level, any given space, binary has only 2 digits, 0 or 1. So we refer sometimes to decimal numbers as base 10, and we refer to binary numbers sometimes as base 2. What this means is that while a decimal number at any given place can have the numbers 0 through 9, it can have 10 different values, and you can grow to higher values by adding another digit, we actually can do roughly the same thing in binary, except in binary, a particular place value is either on, indicated by a 1, or off, indicated by a 0. So you can break down a decimal number by looking at the ones place, the tens place, the 100s place, and so on, and you can take each of those pieces, like the number 137 that we have written here. We could write that number as 100 plus 30 plus 7, and that's actually what we can do with binary numbers as well. We could write the number 137 as 128. We see that that value is on, plus 8, because that value is also on. The others so far are off, plus 1. And so now if we added those up, we would see that that comes out to 137. So decimal digits, the place values in decimal, have actually two pieces of information about them. Is there a value there? If it is 0, for instance, then we know there is no value. If the number were 107, 107, the 0 in the tens place would indicate to us that there are no tens values. Binary has that. It has the zeros to indicate that a particular place value is off, is 0. What binary doesn't have is any levels aside from 1 or 0 at those places. So for instance, in 137, the 3 in the tens place indicates that the tens value is 3, or in other words, that there is a 30 included in this number. Binary is actually a little simpler than that. We have these different places, the 1s, the 2s, the 4s, the 8s, the 16s, and so on. You may notice they're all powers of 2, just like the places in a decimal number are all powers of 10, 1, 10, 100, 1000, etc. So the binary ones are all powers of 2, and they're relatively simple to see what's going on at a particular place. Is it on, because there's a 1, or is it off? And we'll break down numbers using those different place values the same way that you can with a decimal number. I want to make one little hint here that you'll often see if you start to work with binary numbers more, and that is I could look at this binary representation of 137 and I could tell automatically that it's going to be an odd number because the ones place is on. And so I don't have to add up all the rest to know this is going to be an odd number because all the other powers of 2 are even. And so the only way for a number to become odd is for the ones place to be on. If the ones place were 0, I would know that this is an even number. This is something that can often be very useful when answering multiple choice questions about binary things or when confirming that you have the correct result. It doesn't fully confirm your answer, but it gives you a clue. And it will be good for you to pick up on little clues like that all throughout as we go into the process of converting things between binary and decimal. So we can convert any binary number to decimal or any decimal number to binary. Remember that we're limiting ourselves right now to integers because we've already seen that floating point numbers are even more complicated. They have an interesting structure that adds a lot of complexity. So for integers, we can convert from binary to decimal or decimal to binary, and there is always exactly one way to make them equal. So whether you believe it or not before you've seen it here, we always can use those powers of 2 to add up to any number that we would like, as long as we're allowed to grow to more digits. Just like in decimal, you can represent any number you'd like as long as you're allowed to add more digits to the left to increase the value of the places that are available to you. Sometimes when we're representing numbers in different number systems, we will use a subscript to indicate the base system being used for that number. So we have here 137 in base 10, and then 10001001 in base 2. And this is especially important with the binary numbers because if you think about it, that number there could be a valid number in base 10. It will be pretty obvious that most base 10 numbers, like 137, is not binary because you cannot have a 3 or a 7 in binary. But the binary number 2, which is 10, you could have in decimal, it would be 10. 10 is 10. So it's sometimes important to indicate which base system you're currently working in. And I want to reiterate something that I kind of glanced over just a moment ago, and that is that we can count with binary numbers the same way that we count with decimal numbers in terms of structure. In decimal numbers, we can start at 0, go to 1, 2, 3, 4, 5, 6, 7, 8, 9. All of those numbers can be represented with only one digit that represents that 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Once we reach 9, the maximum digit value, we have to add another place. We have to add the tens place. And then we represent the number 10 with 1, 0, the number 11 with 1, 1, the number 12 with 1, 2, and so on and so on. So the same sort of counting system works in binary. We just can represent fewer numbers at a particular place. So we can represent 0 and 1. And then once we can represent those with a single digit of binary. Once we reach the maximum digit value, which is 1, then we have to add another place. And so we grow to having 2 digits. And we can represent the number 2 as 1, 0. We represent the number 3 as 1, 1. And then when we need to represent the number 4, we have to grow again because we've reached our maximum digits in both places, 1 and 1. So then we grow to 4 by having it be 1, 0, 0. We need 3 digits to represent 4. And it will continue on in that way, where if we reach the maximum digit at a particular place, we then have to increment the digit to the left of it. Just like when we reach 19, to get to the next number, we have to increment the tens place and reset the ones place to 0. We can do the same thing in binary. When we reach the number 3, 1, 1, we increment the fours place to be 1, and we reset everybody below there, the twos and the ones places, to be 0. So it looks a little complicated, but it's following the same structure. Now, we've said we can convert between binary and decimal and binary. Let's prove it. Let's do a couple of examples. To convert from binary to decimal, what you can do is you can label each of the place values and then add up the ones that have the number 1 in your binary number. So for example, here, the rightmost place value is the 1s, the next over is the 2s, the next over is the 4s, and so on. So we're moving from right to left, getting higher values, just like in a decimal number. The place values grow as you move left. We've written that out here up and down, vertically, and we see that the 1's value is on. It has a 1. The 2's value is on. The 4's value is not on. The 8's value is not on. The 16's is on, and so on up here. Just like we talked about with the number 137, we can write it out as 100 plus 30 plus 7. Well, look at this. We can start at the highest power here, just like in my example, I started at the 100 for 137. We'll start at the highest place, 128. So we know that this number includes 128 because that place is on, it's 1. Then we look at the next place that's on, that is a value of 1. That's the 64s. So 128 plus 64 is part of our number. Both of those are values that are included in the sum that will represent our number. 32 is not included, so we'll skip it. But 16 is included. So now we have 128 plus 64 plus 16. We see that 8 and 4 are not included, so we can skip them. Some people prefer to write zeros for those places so that you would have something like 128 plus 64 plus 0 plus 16 and so on. I prefer just to write the values that we're actually going to add. So we go all the way down to the 2, which is included. Now we have 128 plus 64 plus 16 plus 2. Now here's a little clue for you. We see that the 1's place is on, so I immediately know this is an odd number. Before I do the sum at all, I know that this is an odd number. I also know that this number is larger than 128, so it's going to be at least 3 decimal digits, whatever I come away with. So we continue on, we get the 1, and if you add all of these up, you find out that this number represents 211. So 211 in binary was 11010011. And we got that by knowing what those place values are. Just like the 1s, 10s, and 100s, there's the 1s, 2s, 4s, 8s, and so on. These powers of 2 that are represented at each place in our number. And we labeled those different place values. And then we just started from the largest one downward and added them up. It actually doesn't matter whether you start at the lowest or the highest, but it's normal to start sort of from the left to the right when we're looking at the place values, the largest and most significant. So we can take any binary number, and we can do this with that number. It actually doesn't matter how large the number is or how long it is, because we can start to label at the 1s and the 2s and the 4s and so on, and just keep going for however large that number may be. Going the opposite direction from decimal to binary, is sort of follows the opposite process. So where before we started with the ones and zeros and we labeled all of the place values, now we have to start with the labels for those place values, and we're going to figure out if it should be a 1 or a 0 at that location. And likewise, where before we were taking all of the place values that were on and adding them up to get our number, well, now we have our decimal number, and we're going to be subtracting away place values from it to figure out which of those place values need to be combined to make up our number. In this case, our number is 116. I've labeled the 100s, the 10s, and the 1s here, but that's actually not necessary for this process. All you need to know is your decimal number, and then you want to know the labels for these different binary place values. You can figure out which place values are going to be required by looking at your decimal number, and you just go until you reach a place value that's larger than your decimal number. You know that that larger place value cannot fit into your decimal number and therefore is going to be 0. So we'll look and we'll see, would this be needed to add all together to make 116? Well, if we start from 1 and go to 2 and 4 and do all these powers of 2, we'll eventually hit 128. And we know that 128 is larger than 116, and therefore 128 will get a 0. But 64 is not larger than 116. So we sort of step down to that value and we say, well, there must be a 64 in my number then. So I will subtract away that 64 from my number because I know 64 is going to be part of the sequence of numbers, the sequence of place values that would add up to be 116. And for many people, this requires a little faith right now because you may not believe that I could take the numbers 64, 32, 16, 8, 4, 2, and 1 and make up any number that's less than 128, but actually I can. So if we trust for a moment that that will work, then what we do is we see that 64 is less than 116. So we take 116 and we subtract away 64. What's remaining, what we still need to build from the rest of our place values, is the number 52. So we have 52 left to sort of cover or to find in these other place values. Well, the next place value is 32. 32 is less than 52. So we know that that one should be on. It will become a 1, and we'll subtract away 32 from that 52 we had remaining. When we do 52 minus 32, we get 20. And so now we have 20 left to find to make up with the rest of these numbers. Well, 16 is less than 20. So we should turn the 16's value on, and we should take 16 away from our remaining 20. That gives us 20 minus 16, which is equal to 4. Now we have 4 left to cover. Well, 8 is greater than 4, so 8's going to get a 0, and we're going to skip it. In this sense, we're not going to subtract it away or do anything with that place value. We just turn it off and say, you know what, there's not an 8 in this number. There's not an 8 in the sum that builds up this number. So that means that the next value that does get a 1, the next place value that does get a 1 is the 4's place. So we put a 0 for 8, we put a 1 for 4, and then we subtract 4 away from our remaining amount here, which gives us 4 minus 4 equaling 0. Well, now none of our place values are going to be larger than 0, or going to be smaller than 0. And so we know we're just going to fill in zeros for any remaining place values. There's nothing else to add up. And in fact, if we pause a moment and look at this number, 64 plus 32 plus 16 plus 4 does in fact add up to 116. We do need those following zeros for the twos place and the ones place, or otherwise when we look at this binary number, we won't know that that digit that's on right here is the fours digit. So we do have to include those zeros or the number is not correct. Just like you have to include the zeros in the number 1000 or you won't know that its place is 1000. So our final number here becomes 01110100. We would write this out left to right, just like we usually would for a number, with the largest place furthest left. We don't have to include that first zero. We could kind of trim it off and keep only the 1110100. It's sort of up to us, and it's up to the system, because remember again that the system often defines how many binary digits are available to represent something like an integer or a floating point value or a character or different things like that. And notice again that this number is an even number, and I see that the ones place is off. So that's another of those hints that we can use to tell that we were correct with our answer. And so this is how, in the system, if, for instance, we had the integer 116, we could represent that integer as a binary number in this way. And likewise, if we had a character that was represented by the code, the ordinal value 116, then we could store that character as this same binary value, 1110100, could represent an integer or a character or a lot of different other possible types of values. And it's up to the system, like Python, the Python programming language, to remember for us, was that intended to be an integer? Was it intended to be a character or a floating point number or whatever else? But what we've seen is that, yes, all of the data in our system can be represented in binary. We may have to use some special codes like the ordinal values for characters. We may have to use some more complex system like the storing where the decimal place should go for a floating point number. But in the end, we're able to represent any number that we'd like, and therefore a wide range of different possible data types as binary on a computer.